So I'd like to thank you again, Saad, for accepting our kind of the invitation, and we are quite happy to host you today for this talk entitled "Binary Code Fingerprinting for Cybersecurity: Application to Malicious Code Fingerprinting." So, Dr. Saed Alrabaee, right? Received the PhD.
Alrabaee, yes.
Yeah, Alrabaee, yes. Received the PhD in Information System Engineering from Concord University in Montreal, Quebec in Canada in 2018. He is currently an associate professor with the Department of Information Systems and Security in UAE, in Al Ain here in United Arab Emirates, of course. So prior to joining this university, he was a visiting assistant professor with the Department of Electrical and Computer Engineering and the Department of Computer Science, University of New Haven, West Haven in the US. He is also a permanent research scientist at the National Cyber Forensic and Training Alliance and CFTA of Canada. His research and development activities and interests focus on the broad area of reverse engineering, including binary authorship, attribution, and characterization, and malware investigation. In this domain, he has published more than 30 papers in top-tier journals and prestigious conferences. So I would like to thank you again, Dr. Saad, and the talk is yours.
Yes, thank you so much. Thank you, Dr. Basso and Dr. Lucas, for the invitation. It's really my pleasure to deliver this talk and also to join the series of the seminar. So I'm connecting, by the way, my laptop to a screen. You might see me looking to other side, but I'm looking at the big screen. So today I'm going to talk about the binary code fingerprinting for cybersecurity application to malicious code fingerprinting. Honestly, nowadays, we always care about the malware analysis, and especially now, the technologies is going on a rise. Everyone's using the smart devices, so we really care a lot about that. So binary code, it's kind of essential component when you need to do a malware analysis, and that's why today I'm going to briefly talk about that and try just quickly to summarize a few solutions that we did in the past. Okay, let me just be sure. Yeah. Okay, so I would like first to start with the motivations. So why we really care about the binary code analysis. So we care about the binary code analysis for several applications or for several reasons. So one of them in malware analysis is really crucial to learn how you can analyze the binary code. So generally, when we are attacked by an attacker, we cannot find the source code. What the attacker can leave on our machine, it's a binary code, where we call it executable code as well. So that's really very important that we understand this piece of file or piece of code or this component. It's why it's in my device. So if we are able to really know about functionality, authorship, about many stuff, that would be great for us as researchers or even as reverse engineers. Now, other one is related to basically vulnerability detection or bug discovery. For example, we are using Zoom, for example, now. So do you have access to the source code of Zoom? The answer is no. So what we do have access to is the binary, okay, or the executable file. So in that case, when we are able to analyze the binary and discover some vulnerabilities, that will help us, hey, Zoom, be careful. We did find these kind of vulnerabilities, okay? And not only Zoom, Microsoft Teams, even the other applications, most of the time, we don't have access to the source code. It's also important for the software copyright. Many times you design a software or an application and you make it public to everyone. And what happened, the bad guys, they just take your code and try to change it. And then they will say, that's my code or that's my application. So the problem sometimes when you ask them, can I see the code? Oh, we don't have the code. I lost the code. Only what I have, binary code. So if you have some good tool or efficient tools, you will be able to discover there is a copyright issues or problems. And of course, other stuff we need to know who's behind the attacks, which is very challenging, but that could be also one of the applications for the binary code analysis. So according to some statistics, as you can see here, there are two figures. The one at the top, which was released in 2017 by basically the AV Test Institute database, they reported that we do have like about 800 million samples. That's the number of malware in 2017. And now if you go to check 2018, 2019, even during the pandemic, the number has been really increased rapidly. So that's really clear why we need to care about the binary code analysis. And you may say that, okay, wait, but maybe it's not me who's targeted. Maybe they target other countries. No, basically when like FSecure Lab, they released statistic like report, it was in 2018. As you can see here at the bottom, the red one, so United States, they were one of the targets, Canada, Italy, so there are many countries. So Europe, North America, even Middle East, South America, so everyone was a target for that. So that's growing trend, make the need for efficient tools to really try to resist or tolerate such massive numbers of samples. So now that's make us to think about how we can really generate efficient and accurate program fingerprinting. So that's really very important, and we need to think about it. Now, when you need to talk about efficient or accurate program fingerprinting, you need to think about the big picture. Now, the developers or the malware writers or whoever, they are writing a code. Now, when they write the code, they have many options. When they need to compile the code, they might compile the code using GCC, using Visual Studio, ICC, or even CLang, okay, if they are using the Mac. And that's not only the things, also the compilation settings could be different. So they might use the optimization speed, the full speed, 01, 02, 03, or maybe they reuse some code from GitHub, or maybe from SourceForge or other public repositories. Now, just imagine that your code is not pure. You write some part of it, someone helps you, and you have reused code, and you are using different compilers. And at the end, what we will have a binary code, the executable. That's the case. Now, when I look at the executable weight, that's very challenging. I don't have any information related to the strings. I don't have any information related, for example, to the function names or anything related to the actual control flow graph or the data flow graph or whatever, right? So that would be very difficult. Now, is it that if we really think about to analyze a binary code, is that task easy or challenging? Basically, is a challenging task. Now, to do that, first of all, you need a knowledge and security. So why you are going to analyze it and how you will analyze it, what you're going to use, from where you will start, that, of course, you need to know based on your knowledge or based on your expertise. And lack of semantics. So when I have a source code, I give you a source code, I ask you to understand the source code. If that will document it, it doesn't take you a lot of time to understand. However, we have a problem. The problem, when it goes to binary, especially if we are using release mode, not debug mode, or if we strip the binary from the debug symbols, when you look at the binary and then convert it to assembly, you will not find that strings, you will not find that, for example, function names, you will find the new functions. So it's really, this, I would say, is a big of mess, okay? Now, of course, that's error prone. So there is a chance that you do a mistake. You may say this is a malware or this is a benign. There is a chance that you did a mistake. Or when you analyze, you discover is used that functionality, it comes from there. So still there is a high chance to do mistakes in here. Now, time consuming, everyone will agree with you when you ask about binary code analysis, they will tell you that's really error prone and time consuming task. Okay, and that's why we really always think about efficient, about efficient solutions. So one of the things that we really need to care about, or we need to think about it, okay, we said how we can have effective program fingerprinting. So we start thinking about, number one, we need it to be a unique and compact representation of the functionality of a binary program. So number one, when you have a piece of code, you need to know what is the functionality of this code. Is this binary code, if you run it, it will, for example, steal your credential or spy on you, or it will do other maybe bad task or something, then, oh, wait, yes. So try to think about some representation. It helps me to know what is the functionality of this code. And then we need to think about, okay, you need to know who's behind this code. I mean, who are the authors? Is it from which country, origin, etc.? Many things we are looking for. Now the question, how your features will be enough to discover the functionality and then discover the style of that author. So in that case, I would say, hey, this code comes from the family of that, or from that malware family, okay? Or this code, it comes from X or from Y, and how I know that, because I do have features, and that features detect the styles of the authors, or the coding habits, or whatever you need to call it. And another problem now, of course, the bad guys or the malware writers, they don't take it that much easy. Okay, they always read what are the existing tools, what they do have, and then they try to resist, they try to evade, they try to find a way. One of them always, they use encryption. You know, when you do have an encrypted file, you will not be able to decrypt it until you have the right key. So when most of the malware writers, they use their own customized encryption algorithm, and that will be really a problem. So we need at least to think about some changes, at least compilation settings. We can tolerate that one. Changing compiler, we can tolerate it. So, you know, there are many things. If you think at the beginning, I need to handle all the challenges, for sure you will fail. So we start with basics one, we call it code transformation methods, like the polymorphic techniques, changing compilers, compilation settings, etc. Now, to start with the authorship attribution, we were thinking about, okay, I have a binary. I need to ask myself, or ask the AI, or ask anyone, hey, could you tell me who did design this one, or who basically did write this code? Oh, you know, let me check. So we start to think, okay, when I write a code, a source code, and then compile it, then I have the binary, and the binary converted to assembly, at least to make it a bit easier to me to understand what's going on. We found there are many new functions are appearing at assembly level. So if you have, let's say, according to the literature, one source code function, it will be represented by about 70 functions at assembly. So let's say you have 10, it will be kind of, let's say, 700s. Of course, it depends on the compiler, depends on the settings. Sometimes it will not be that number. But if you don't use any optimization and you use the debug mode, then you will have kind of this number. So now when we try to analyze it manually at the beginning, we found there are functions which is related to compiler. There are functions which is related to the library. So, you know, when you write a code, you will sometimes you use some packages, let's say in Python, but in C++, you include some libraries. Or sometimes we have the DLL, the dynamic loading libraries, right? And sometimes you reuse some functions. So if I'm reusing a function from someone else, I cannot say this is my code. And you cannot say, oh, I figure out this is your code and you are the author. Hey, this is a reused code. And then we have also functions, they could be modified, but which is available to you, like in GitHub. So you go to GitHub, you find the code, which is encryption algorithm. You take it, modify it a bit, and then use it in your code. So basically, this is somehow is not your code. You modify it a bit, and then you said, hey, that's my code. So the only one that can help to know who you are is user-related functions. So at the beginning, when we were thinking about a solution, we did say, hey, why we don't try to filter out the unrelated functions? So any function related to compiler, just take it out. Related to library, take it out. Reuse, take it out, and so on. But now the question, how you gonna know this is a user-related function or is a computer-related function? Okay, for that reason, so you need to think about different tools. One tool, identify a compiler for you. So at least I know what is the compiler was used for this binary. And then how you can identify the free open software source code packages, because you may modify it a bit and add it to your project and say, that's my code. And that will be misleading, right? If someone again reuse the same code, I will say both guys, they write the same component or they are the same authors, which is not true. So functionality, that's important for many applications, malware triage. If you need to know from where I have to start, oh, wait, you are giving me that number of samples and you ask me, hey, analyze them. So let's say you have 10,000. So from where you start? Do you start from number 1, number 10? So if you have a tool that it tells you at least on the fly, hey, here is the ranking. So start with top 10. This is the top 1, that's top 2, top 3, 4, and so on. That will be something really important. The main or the ultimate goal to know who's behind the attacks. That will help all of us at least to discover the bad guys. So authorship characterization, if we are not able to know who's the author, which is the case, sometimes they are a group of authors, they design a malware sample, or a country who supported a team of developers to do a code or to do an attack against another country because of political reasons or something. So, you know, that will make it difficult. So then we were thinking about maybe authorship characterization, where you can simply say this code is written by a group of developers, not one. This one was written by expertise. This was written by beginners. This was written by students for assignment. This was, for example, highly structured threat because it's clear, was well written, following good standards, etc., or is an APT. So, you know, there are many really things you can think about the characterization. Finally, the vulnerability analysis. So where it's very important in our daily lives, we need to know what is really the vulnerability or what's the problems or what's going on. That's really very important. Now, reverse engineers and security experts, they will appreciate everyone who's really trying to design a tool. So generally, whatever they have tools, they try to use it in their error-prone tasks. Okay, so for example, OLEDBG is used nowadays. AIDRC is used by most of the researchers. AIDRC is not a free, but is still common. This assembler framework is used. Paradigm, that's a good one, and the good news, the authors of this one, they make it available for researchers, but it's a Linux based. So if you need to have it for Windows binaries, you need to modify it, or maybe you need to change or try to use other APIs. So, but still the code is available. So that's how they look at it. So if you try to identify a compiler and that tool is efficient, they're gonna use it. If you have FOSS packages, they're gonna use it, and so on. Okay, one of the questions maybe it comes to your mind, hey, you are talking C, C++, but nowadays we use Python, we use Java. Now, according to the literature, most of the I would say the attacks, they are based on C, C++ code. Okay, so I think one of the articles that I read a long time back, maybe 2019, they did say 80 to 90%. I would say 80% of most of the attacks. I mean, I would say the files that they found was a binary which was compiled from a C or C++. Is there any attacks could be written by Java or by Python? It could be, but you know, we don't have, when you compile that Java code, you have a bytecode at the end. So that bytecode should be converted to a binary. And that's another problem and another issue. So here is just an example. So one like very simple code or a program is just printing an array in a which size of 32. So it was compiled by using CLang, default optimization, GCC, and ICC. So if you look at the control flow graph, and the control flow graph as source code, we can generate it by some open code or by open tools, open source tools. But here we try to extract it through AIDRC. And when you look at this one, you can find there is a similarities. So if you look at the basic things, the number of basic blocks or the number of nodes, the number of edges, how the shape it looks like, there are some differences. However, you may tell me, but still there is some similarities. If you look at the ICC, GCC, the shape somehow looks the same. But if you try to change the optimization, if you try to change the version of the compiler, completely it will be different. If you use some obfuscations techniques like flattening or CFG bogus, so the CFG will be completely different. Okay, so here I just show you that with a simple program, how many basic blocks we do have when the compiler is changed. And ICC itself, or GCC or CLang, if you change also the optimization, the control flow graph will be also different. And I'm pretty sure you did hear about also function inlining. If you have a small function, will be inlined with another large function. That's also one challenging when you are dealing with a binary code analysis. Now, with the main related work, to not give more details, I will just go briefly about them. So for the fingerprinting binary functions, there are too many works on this domain. Now, one of the nice work, which they create kind of search engine, is a Tracelet and Rendezvous. And Rendezvous was the first try to generate a binary search engine. So what you do, you have an assembly code, you put it on that engine, you click on search, and it will match it with some source code packages or with some existing packages from the database. So it will tell you, hey, this assembly code is an encryption function or is hashing or compression or whatever, okay? And unfortunately, since 3 or 4 years ago, the engine is not working anymore. The code is not available. But I mean, the ideas, the features, the paper is clear, and it's really very nice article. You can simply read it and learn also more about the concepts that they did use. Tracelet was a nice article as well, and was published in one of the top tier conference programming languages, PLDI, I think 2014, if I'm not mistaken. Rendezvous was 2013 maybe. Tracelet, the code is available. You can either send the author's email or you can find it in GitHub. It's a very nice one. Again, these two based on the fragments. Sometimes we don't have the complete code or the code is damaged or destroyed. Then I need really to know the fragment is because I need to know what was the file about. So you can use such search engine. Now, the other part is graph-based. They try to deal with the structural similarity. One of, I would say, one of really nice article, which I call it, is like the mother in this domain is BinDef. So the BinDef was written by Thomas Dolian. He's from Germany, and he was working in Google. And now I think he has his own company a few years ago. So it was available. I mean, I'm not sure now, but it was a very nice. You have a 2 binary, and they try to find the differences between the 2 binary. And it gives you some probability values, why they are different, and what is the probability, which I would say is like a confidence value. Another one, BinSlayer, that's a nice one. It was on top of BinDef. I mean, they modified BinDef. And this one is somehow they use more features, add more semantics to the structure similarity algorithm, and they have a good results and they improve the BinDef. And there are many other works. There is a work in the USA, they add deep learning to BinDef and they call it BinDeep or bin deep diff, I think, if I'm not mistaken. So yeah, that's also nice. So there are many basically researchers, they work on it and they still work on it. So top tier conferences like Usenix, SMP, CCS, and NDSS, they always accept papers in binary code. So the other domain, binary authorship attribution, they are single author articles, and there are multiple authors, article where try to discover the single author of a code, but there are another articles they were designed to discover if that code was written by multiple authors. And with a single author, the first article was designed by Rosenblum. It was in 2011. The code also was available. The guy, he was very helpful. When you ask him, he replied to you in case if you need to try with it. After that, we tried to design a tool based on Rosenblum, and we were able to improve the accuracy. And for a presence of multiple authors, we do have only one article so far, and was published in 2017, because it's not easy, okay? And in this case, they were identifying the author at basic block level, okay? So that's just to briefly describe. And of course, there are some dynamic analysis. So there are Plex. It was published in Usenix, IBM Hunt. That's a nice also tool. So there are really many good tools. Now, for us, when we were thinking about what we need to do in binary code analysis on cybersecurity, we were thinking really about building a cybersecurity fusion center. So this center can accept any type of inputs, binary code, Android application, industrial control system binaries or firmware images, network traffics, firm images, darknet, dark webs, I mean, software binaries, cyber attack information, any inputs related to cybersecurity. The goal, we need to accept it by our center or our framework. And then we will use or devise state-of-the-art algorithms, analyze, and then come up with output. So the outputs, we are looking to tell you about the authors, if possible, what are the vulnerabilities or bugs, which is kind of ethical hacking, what are the reused code parts, if it's really a malicious code or benign, what are the characteristics, verify some results, Android. So there are too many, basically. Now, what we did, to think about it, we have some collaborators from worldwide and also in UAE, UTSA, Texas, San Antonio, they have a cybersecurity center. They are collaborating with us. And also the Tsinghua University in China is one of the top universities in China. There is a machine deep learning AI lab. The director of that lab was also happy to be part of this center. One professor, he's in data mining in McGill University in Canada. He was also happy to be part of it. Concordia, Georgia Tech, and also New York, Abu Dhabi. And we are open, of course, for more collaborators. And now we already did the work with UTSA and Concordia, McGill. Next step, I think we are going with Tsinghua University and UTSA. Georgia Tech, we are working in firmware images. So we are trying to do our best to really have a big center, that center to help the community and to help the worldwide. Now, what we did so far, we tried to do some authorship attribution. We have some tools, we make it available in GitHub. We discover some vulnerabilities. We try to discover some reused code. We try to discover some software copyright problems and also some software violations if there is any breaking for policies. We did use deep learning, we use hidden Markov models, data flow analysis, graph theory, Bayesian models. That's just a big picture, okay? So we completed some tasks and we have ongoing tasks. Still, we are doing our best to really have the things to be completed and of course updated. So the objectives that anyone would like to work in binary code analysis, they will have these short-term objectives, regardless what the domain you would like to work on it. Generally, it looks like this way. Now, the most important things we need really to know what are the features I can use. So do I use syntax features or semantic features or structural features? So which one you're gonna use? And the feature is very important. You may tell me, but wait, maybe I use deep learning. I don't need to do any feature engineering things. Yes, deep learning is used, but still now very recent works, they really do analyzing by using natural language processing. Okay, so they try to apply natural language processing on assembly. They try to apply even machine learning. Still, they use that one. They try even to apply some distance metrics. So deep learning, it helps in some cases, but in some cases it doesn't help. Now, the other things, once I identify what the meaningful features, or we basically define the new features, we need to think about how really I can have a system to extract these features and match them. Generally, we may have exact matching or inexact matching. So exact matching, you have signatures like antiviruses, and you just try to check if it matches, hey, this is a virus. Otherwise, no, that's not a virus. Or inexact matching, where you use distance metrics, or use anomaly detection, for example, or use machine learning, or you use even, of course, explainable machine learning or AI to know why this is a malicious or that's a benign, or to give some weights to have some voting systems. Now, once we are able to extract and do the matching, we need really to think how we can be scalable, because the features of the malware analysis in general, it's really a big data problem. How you going to manage and how you'll be able to really treat and deal with these data, and how you're going to be accurate. I mean, how your tool will be very accurate to discover if this is a malware, or who's the author, or what is the functionality, or even what is the other reused code, or etc. And after that, you will apply to the problem that you are trying to solve. So let's say I need to do authorship, or I need to do functionality. We always do in binary. Most of the existing researchers, you try to use it in non-case. So you use some existing data set. After that, you try to apply for some use cases like malware analysis, for example. Because when you know that at least it's doing well at the binary code, the normal one, then you try to think, okay, let me go with the malicious to really try to know about that. Because one of the challenging, unfortunately, we do have the grounded truth. Most of the time, we may not have a grounded truth to test our framework. So that's why we try to test on some existing binary code in GitHub or other places. So we have many solutions, and because of the time, I don't think so I will be going to cover all of them. I will try to cover the first one, the binary authorship attribution, and the second one. So with the first one, we came up with two solutions. Basically, there are three. There is one recently get accepted. So OBA2, which is, an article was published in Digital Investigation Journal. And the other one, Ben author, was published in AIDRC. And AIDRC is one of the top tier European symposium in security and privacy. And also this, we received an invitation to extend the article and publish it in GCS, Journal of Computer and Security Journal. I will go with OPA2. We call it an onion approach to binary code authorship attribution. Wait, onion? What is the relation between food and the reverse engineering, etc.? Okay, why we were thinking about it, I will let you know. So first, we know the onion has many layers. So this tool, we have a different layers, layer 1, 2, 3. And when we look at that layers, we have a purposes to design it in that way. We need to remove, let me just use, yes. So we need to, for example, do code filtration. So we need to remove the code which is not related to our users, because I'm doing authorship. And then I need to do another layer where I just do syntax-based attribution. And then I need to do semantic-based attribution. Now, what the challenges we faced, what was the problem, etc., how you will validate your tool, and how you will have a good data set. That was really challenging, and still is challenging in binary authorship attribution. And finally, heterogeneous environments. So you can use different compilers. You can use two compilers at the same time, or they call it tool chain compilation. You may reuse some code. So that's really heterogeneous environments. Even now, GPT can write a code for you. Now, what if you just write a code now based on GPT? Hey, GPT, write a code for bubbles or for do X or Y. And then you modify it a bit. This machine generated code is challenging, okay? So why we call it onion? Because, when you have that onion, you remove the outlier, and that's why the outlier here is code filtration. So we remove the outlier just to remove unrelated functions. Then we go a bit further, which is the syntax extraction, and the juice will be a semantic. So when you go to inner ones, that's really the actual onion, or the one that you feel the taste of that one, right? So that's why it came our name, onion approach. So by looking at the general picture, so we have a set of programs. We do abstractions by extracting features. We train our model, and then we classify it, okay, based on the labels. So this is author 1, 2, 3, 4, or whatever. We have used data set from our university in Canada, basically, and we try to remove the names of the students for the privacy things. We get the approval from that ethical committee that we can do that. They accepted. And then we were able to train different classifiers, SVM decision tree, Bayesian, many classifiers. As I remember, SVM was the best. So let's go talk in details about it. So the first one, filtration, where we call it stuttering layers. What we did in this layer, basically, when you have a source code, you compile it. So when you use a compiler, the compiler has compiler-related functions. And you may use some libraries. Let's say you use ctime, vector, whatever that library. Also, some library-related functions are there. Now, we take the advantage of AIDRC, which is called the flare. And that flare is part of the AIDRC, where we use that one, the signatures, apply it to our code, and apply the signatures, and then identify here the functions related to compiler, here the functions related to the libraries, and so on. Now, the problem, when you have the binary code and you need to convert it to assembly or disassemble the binary to assembly, we have problems or challenges. One of the challenge, where the starting point. We have code and data. So from where the function starts. So the boundary functions, that's a challenging. And unfortunately, AIDRC, we discovered later, has a limitation for identifying the function boundaries. You need to tell me here the beginning, here the end for function 1. Here the beginning, that's the end for function 2. If that's not accurate, then your results will not be accurate. So after we apply, we know these kind of functions related to compiler libraries are not needed. So we just filter them out. Now, some people, they start debate and argue, hey, let's say I always use a Visual Studio. I don't like to use ICC. I don't like CLang. I don't use GCC, for example. So that could be a habit, right? On the other work, yes, we consider it as habit, but in this work, we just filter them out, okay? So the other layer, where we call it code analysis layer, where it's related to the syntax, we try to think about some source code, keywords, or some categories, and we try to think, you use what? So, some of you maybe like to use if, some of you use if else, some of you like to use for loop, some of you use while, some of you use a switch. You may use some specific libraries. So we try to think about, could we have a signatures at assembly level? Honestly, it was a very challenging. We were able to build a dictionary, but that dictionary, when you change the optimization, it doesn't work. So that's make our life tough. Okay, when you change optimization, you change the compiler, you try to play with this, that would be very challenging, okay? But if you do it for the same, like here, Visual Studio 2010, and optimization, I think, was 01, it was perfect. We were able to discover. But other than that, it would be a problem. So if we have a tool, that tool can discover the compiler, and the compiler was a Visual Studio and Optimization 1, that will work very efficient. But again, if the malware or the bad guys or the adversary, he knows this disadvantage, simply he will just change the compiler or will change the compilation settings. And then our tool will not be able to discover anything or any habits. Now, the other one, which is semantics, register flow analysis layer. So what happened, we were conducting questions with some people who writes code, like code, heavily code, like design many projects, etc. We conduct an interview with them, and we try to ask them, do you think your coding habits or traits will be reflecting in how you use your variables, local variables, static variables, or global variables? The majority, they said yes. Sometimes I like to use global variables. I never use it. I know some cases you need to use it, but sometimes I don't like to use it. Some of them, they use pointer to modify constant. And generally, you don't modify constant, right? Because that's why you call it constant static variable or something like that. So we were asking, and we said, okay, let's think about a new feature, a new graph. We call it register flow graph, RFG. And what we did, we generally the assembly instructions or the normal control flow graph is just instructions, move, push, add, etc. Here we start to think we will create classes. So arithmetic, logical, generic, stack. Within arithmetics, I will add, subtraction, multiplication, division, etc. With logical, we have the shift, XOR, or. With generic, move, stack, push, pop. So we try to have groups, and then if you find one, then that's class 1. If you find only logical, that would be 2, class 2. But if you find, let's say, all of them, that would be class 16. So we have a big table for these classes. But now the question, wait, classes for what? That's a bit confusing. Okay, now when we did ask, remember, we are trying to do authorship attribution. So we felt when you try to do comparison, you may do it in a different ways. For example, you may do it in trying to use different way, how you pass arguments, how you compare. So in that case, we care about only compare instructions. So if you have this code, then we do backward and of course backward forward analysis. We find compare. It has 2 registers. We care only about registers because we believe the registers represented the variables. So we take each register and we see how it's basically manipulated. And based on that, we give a class. So when we go ahead with the first one, ACI, for example, was manipulated by, let's say, push. We call it a stack, and then move, which is a generic. If you come to this table, so generic should be 1 and stack should be 1. So 1, 1, but should be the other 0, this one, so it will be class 14. So then here we color this one and it will be class 14. And if you go to the green, you can find you have arithmetics, you have then generic and again arithmetic. So that's one will be 1 arithmetic, 1 generic, which is class number 6. Then we generate the RFG. And at the end, once we have all the RFG, we hash them to be fast when you do a lookup, when you need to search. Now, when we do the implementation, we used PostgreSQL. We use, by the way, we write the things in C++ code. We didn't make it on GitHub. We make it just open the request. If someone asks, we can share the virtual machine. Why we did use PostgreSQL, our case was scalable, was fine. But later with the new projects, we used MongoDB and Cassandra in some cases. The other one, Ben Author, where is extended version, we start to think more, wait, why we need to only rely on something, and that's maybe it will not be really resist, or it will not be stable or robust enough when we change the compilers. We were thinking about, could we really define coding habits? Now we try to do questionnaire, we try to do interviews, and we make it now worldwide. We send it to different countries, different people. We check in GitHub, we check everywhere, and we ask them. And now we found there are many habits, but we don't know if we can catch them at binary code or not. So we group them to skills, expertise, preferences, code organization, code quality. So based on your skills, that's why you have that habit. Based on your expertise, that's why you have that habit, and so on. So we try to search and we try to categorize them. And if you remember with filtration, we were just taking out, now we put it in a new category. We call it the preferences. So where we don't have a compilers, okay? So here I would say the approach overview for bin author. So we do have a filtration component. When you have a target file, you compile it, or it's compiled already. So you filter the functions library related, compiler related, and that's user functions. And then we send it to other components where we call it choice construction. Choice construction is about these code habits or code traits, okay? So we call it code choices, that's the name. And then we map it with our database and we identify the author. That's how we can, we did it, okay? And here we didn't use deep learning or machine learning. We just came up with basically a probability that we give a weights, and then we try to identify or discover the author of that code. Now, what are the habits that we have or choices? One of them, we call it general choices, where it's about code organization, function termination. Now, in source code, it's really easy to know if the code organized or not. But when it comes to binary code, is difficult. Then we start thinking, could we have some ratio equations? Here I just bought some samples. We define ratio equations of more than 20, 30 equations, like the number of bush over the length. Length here, we mean the number of instructions on the main function. Number of bush to, here we are trying to see the ratio of local variables in user-defined functions to the main function, just in order to discover if there is any really habits, okay? And also the calls, do you have the habit you always have many functions in your code, or always you try to minimize as much as you can? But again, here there's a problem, the function aligning. And that's why we did use data flow also to discover this function aligning. The other one is function termination. How you terminate your function. Do you really freeing memories? If you use the dynamic allocations or heap allocation, do you free after you allocate or not? Do you, for example, printing clock time or printing to a file? So what the habit you do generally when you terminate your function? And the other one is about variable choices. If you remember, I talked about register flow chain, register flow graph. Here I'm trying to extend it. So we check every register and we normalize it, reg 1, reg 2, in order to avoid the compiler normalization, etc. The changes. And then we try to see what is the longest chain, what is the minimum chain, how many chains we do have. That we feel it might show us how you manipulate the variables. So another one is about quality related choices. When you write a code, are you following some standards? Like there is a standards for C, C++, which is available, anyone can look at it. So we did our best to build a dictionary, how we can catch these standards at the binary. Many of them, they were challenging. Some of them we were able to discover. I know there are some teams from Ohio State University, they have a binary tool, they discover data structure algorithms. And that's something very nice, and maybe we need to look at it. But I mean, that would be something interesting. So, you know, every part is like a research area or research domain. So we try to discover something. Some choices, we call it embedded. When you write a code in general, some habits will be there, but really we don't know what is that. Are you reusing some code which can be discovered by structure choices, or you are following some something in your mind? I will start in this way, define this, change this, do that. So some of them, we look at the shape distribution, it looks somehow the shape similar, but we really don't know how that comes. So it is like embedded choices or something that we're not able to discover, but we try at least to see the shape of the code, control flow graph, data flow graph, programming flow graph, or even something more. With evaluation here, we did use different data sets from GitHub. Some of them, they were written their name. Some of them, they use nickname. And we use Google Code Jam Contest. Is a very nice place that you can use the data set, but now is not available, I think. We use it from 2010 to 2018, I think, the data set. The good things with this data set, you have the country, and you have the language, which language is written, and you have the source code, by the way, and also they give you two tasks. One, you need to write a solution in on the longest line of code, and one with the shortest line of code, and different countries, but now I think it's not available. We tried to search a few months ago, we didn't find the code that's available. I think the server is down. Also, blended source code is like somehow GitHub, and the graduate student code, where we try to always preserve the privacy. We always remove the names or remove anything, okay? And we just give a name, like author 1 or author 2 or etc. Here, the author classification, we give a weight for each choice. If you remember here, we have general choice, number 1, variable choice, number 2, quality related choice, number 3, embedded, number 4, structure, number 5. That's why we do have 5 here. And the weights at the beginning, to be honest, it was manual. Like, okay, based on our experimental results, give this 20, this 30, but we found that's not good. We tried to do something else. What we did, we used logistic regression, and we just try to identify the author based on based on that choice. So choice 1, oh, it gives me that result. 2, it gives me that result, and so on. Based on that, we give the weights. I will try to speed up because of the time. We applied to some malware, and we found some similarities in terms, we believe, on authors, like Bunny Babar, generally they said it's written by same team, Stocknet Flame, written by same group, Zeus Citadel, etc. Here some of the examples when we analyze it manually, what we did find. The other one, binary code fingerprinting. I'm not going to talk about the second one. I will talk quickly about Sigma to give you just, if you can ask questions. So one was published in Digital Investigation. The other one was an ACM transaction on security and privacy. So the Sigma is, we try to build a new graph in binary. We call it SIG, Semantic Integrated Graph. So what we did, we combine 3 graphs together. So we try to combine control flow graph, data flow graph with register flow graph, and we generate a new graph. And it was useful for reused function. So we were able to have a good accuracy. We use inexact matching. We didn't use any machine learning. If we take the bubble sort as an example, the general control flow graph, it just shows you boxes, which are basic block, and edges. If it's true, go there. If false, go there. If no condition, just go to the next block. So if you look at it, here is for the bubble sort. So number 1 to number 9, they are arbitrary numbers. 1 doesn't mean anything. It means just the first basic block. And number 2, second, third, even 9 could be 4. You see here, numbers has no meaning. Now we apply coloring to this CFG, and then we generate a new graph. So the problem with the normal CFG, you may have same CFG for different functions, and that's will create a problem. Now with the function call graph, we found there is internal call, external call. And we noticed that if you go with internal calls, they are really related to something else. So you cannot take care of it. So we care about external call. So let's make it more weights and ignoring the internal call. So we add more coloring to these nodes. So that's the big picture. So you do pre-processing, extract the traditional classical features, apply coloring merging, we generate ICFG, CFG, merge RFG, we merge them. This graph is a new. That's novel graph that we did it. And then this graph will be used for inexact matching and exact matching. So either you so here the CFG we converted, you can see we reduced the number of nodes, now the number of edges. Here for the function call, as you can see now, API calls, we give it a color. Now we color the nodes. Also for the merge, now we generate many new classes, new categories. So now when we have it, the new figure has more semantics. And finally, we convert them to one graph where we call it SIG. And now when you have the SIG, like for bubble sort, the motivation example, as you can see, I compare in two things. Either I use exact matching or we use inexact matching. So we generate the traces and then we do graph edit distance comparison where you calculate the cost, how much you need to pay to convert from this figure to that figure. And the results was very interesting when we applied to Zeus and Citadel matching. Work in progress. We are working in authorship characterization, which is somehow polymorphic malware analysis. We are trying to use image processing. We are using now natural language processing to do multi-dimensional fingerprinting, authorship verification and authorship attribution for Android, fingerprinting firmware vulnerabilities. We have now paper under revision. We try to discover vulnerabilities in routers firmware images, and we are having also work about characterizing the cyber criminal's personality and also authorship verification. For this authorship verification, now we are working on it. We have good results. We use formal methods. So the API calls, we model it by using model checker, and then we have a solver to tell me, yes, this is the author A or not. So this will be built on the existing binary authorship attribution. Sorry for taking that much of time. I did my best to complete the slides. So I'm open for any questions. If you don't have any questions right now, you can email me. This is my email at any time. Yeah. Thank you so much.
Good. Thank you so much, Said. Thank you so much. It was quite insightful and clear. We have one question from the audience. Can this be used to estimate the amount of Stack Overflow copy-paste in the proprietary software?
Let me just read the question. Let me open the chat.
Yeah.
Can be used to estimate the amount of the Stack Overflow copy-paste. I think that's really a good point. Honestly, since that one, it will, that will be very hard to answer. But according to my expertise in this domain, that would be very challenging. So we did try maybe once just to work with that. If you do some copy-paste, but we were not able to discover, or even we were not able to find any good or to give good results in that. So I think that will be very challenging. I don't think so we can really do something in that, but that's something very interesting. I think we need to look at this one.
Okay, we have a second question here on live. Does the cost function take into account the changes in coloring, like for external, internal, etc.? So
that's a very nice question. Yes, yeah. We do add to this cost function many parameters. One of them is about the external, internal things. Yes, because as I said at the beginning, was manually, and then we use logistic regression, and then we try to modify based on the inputs. For example, changing the compiler, changing the optimization. For example, if you change optimization, which choice or habit will be affected more? So that's also was one of the factors we take into our.
Yeah, he was like one of the Bilal is asking about like the weights, how they are computed.
We use logistic regression.
We use
the coding habits only one, let's say general one, and we apply it in our data set and we record the accuracy. We go with the second one, third one, and we saw, and then we change compilers. We again use them, we record, and finally we take the average, something like that. Yeah.
Okay, so thank you. I have one more question. Is it quite important to consider, I mean, the performance implication, I mean, of using the filter function on large data sets, I mean, as it may impact the overall like efficiency of the code?
Yeah, I think that's a good question. What we did, we tried to, I mean, it's like a trade-off. When we remove the filtration, we measure the false positive rate. And then we ask ourselves, could we tolerate that false positive rate? So honestly, in some cases, the false positive rate was above 10%, which is to us very high. So yes, that time, or I would say the overhead, it takes time. I'm not saying it doesn't, but when you reduce the false positive, that will be worth it to spend that time.
Okay. Thank you so much. Thank you so much. I think, yeah, second question. So how would you determine the threshold in matching? Like it depends on the sum of the weights multiplied by the difference, for instance.
Yeah, honestly, again, that's really a very nice question. I like the type of the questions because that's what we faced. Like at the beginning, we said, okay, let's put a threshold value, which is, let's say 0.8, the probability. But we found it's not what we are looking for. What we do, we rate them. Number one is this, number two is this, number three is this, and here are our scores. And now when we give it to the, let's say to the security experts or reverse engineers, they will start with the first one. So the goal is not like to ignore something. We need to basically just try to rank them. So threshold value, we don't have really a fixed threshold value. We just have it. We try to run it. We calculate the probability and we give that value to the expert or someone. Hey, this code is similar to code written by myself, 80%, 70, and so on.
Great. Thank you so much. I think it was quite insightful and clear talk. Thank you very much again, Dr. Saed.
Yeah.
And we are quite happy again to host you today.
Thank you so much. It was really my pleasure and honor to be talking to you guys. Thank you so much.
Thank you so much, and keep in touch.